Hello everyone, I hope that you are fine. Welcome to another session of Robotics Lab. Today's lab is about path planning and path search. For this lab, it is expected that you have a basic theoretical knowledge about graphs and Dijkstra's algorithm. So my recommendation is that you should listen the lecture about the path search algorithms, especially for the Dijkstra's algorithm, how it works, what are the inputs and outputs. So for this lab, the knowledge from the lecture is really important. So what we're gonna do today is we shall do path search using Dijkstra's algorithm in Matlab software. Let's proceed. In today's goals, what we are gonna learn today is, the first thing is we shall try to understand the concept of adjacency and cost matrices. After that, secondly, we shall learn about how to make a graph. You remember in the lecture we studied about the graph. A graph consists of edges and nodes. But in this lab work, we shall finally try to implement and try to make a graph. In the third step, we shall use Dijkstra's algorithm to find minimum cost or shortest path in the graph. So the graph we make in the second step, we shall then we shall use Dijkstra's algorithm that is already available in Matlab, and we shall use it to find the shortest path from start to your goal location. And finally, we shall learn how to plot the results for visualization purposes. So the Matlab code for Dijkstra's algorithm, it is available on this link here. You can copy paste this link. You can just go to their websites, MathWorks, and then you can download this code. Maybe you have to sign in or log in, and then it's free to download, and you can use it. And this code is written by, this is the author of this code. And I shall also include the link in the YouTube video to download this Matlab code. So okay, this I think we can do. This we can do later. Okay, so I have already downloaded this code. It's called Dijkstra's.m file. As you can see here in my current folder, it's already available. And now what I have to do, I have to make a new script, and I save this script. Let's say path search di Dijkstra. So I think I need to switch my keyboard from, okay. Okay, this is the name path search Dijkstra, and we save it in our current folder. Okay, there should be no space, so let's remove the space and try again. Okay, it worked now. So this is our editor, and here we have workspace, and this is our current working folder, and here we have under command window. So let's start the coding. So first we write clear all to clear any variables we have, and after that we define nodes. So you remember what are the nodes? Nodes were just points having some coordinates. So I mean, if they are 2D, two-dimensional, then they must have x, y coordinates. So let's say the node is 1, 1. First node is located at x coordinate 1, y coordinate 1, and then we have a second node that is located at x-axis 3 and y-axis 4, and then we have a third node that is located at x-axis 2 and y-axis 3, and the fourth node has a x-axis of 4 and y-axis of 3, and the fifth node, let's say it is x-axis 5, y-axis 5, and then we close the brackets. So these are the nodes we have. So nodes are just points and having some xy coordinates. So these are the first one is x coordinate, and then y coordinates, and then there is a semicolon which shows that, okay, now comes the next row. So if you see that this is an array. This is an array with 1, 2, 3, 4, 5 rows and 2 columns. Okay, if you try to be let me try to explain it here like this. The help of pointer, maybe, yes. So when we define nodes, we are defining like this x and y. 1, 1, 2, 3, 3, 4, 4, 2, 5, 5. So we are defining like these are the nodes. 1, something like this, this, and this, and this, and this is our, let's say, x coordinate, y coordinate, x coordinate. So these are our node. So this is our first node having coordinate 1, 1, this n1. So I'm making it roughly. It's not exactly what because it's just an example to show you. So this is a node here, and then we have node 2, node 3, and similarly let's say the last node N5 here, this one here, it has a coordinate. This is also a point with coordinates 5 and 5 and 5. So these are the other 3 nodes with different types of coordinates. This is, we have y-axis and x-axis. So when we are defining in Matlab an array, so we have an x coordinate and then y coordinate, and it means we have 5 rows and 2 columns for x and y, and 5 rows for 5 nodes. I hope it is clear now. Okay, so here we have done this. So these are the nodes with x and y coordinates, and we have total 5 nodes we have defined. Should I mention also here? Okay, after that we have to define the start node and the goal node. So start node is, let's say first node is a start node, which is this one 1 1 here, and then we have goal node, which is, let's say the last one, the 5th node, is the goal node or the target node. Okay, so we have defined it. So this is the start node and this is our goal node here. And after that we have, now we have to define adjacency matrix. So what is an adjacency matrix? Adjacency matrix, it is used to define the relationship between one node and other node, whether the nodes are connected or not. So this is something we call it adjacency matrix. You know that for the graph, it is important that the graph must have nodes, as well as it must have also edges. Okay, so for example, this is a graph we have. Let's say this is a node, and then we have this node here, and then we have this node here. So this is N1, this is N2, and N3. So now we have already created a list of nodes, okay, in the Matlab. Now we want to tell Matlab that which nodes are connected to each other by edges. So how can we do that? Let's say node N1 and N3 are connected, and node N3 and N2 are connected. Okay, so how can we do that? One way is doing it using the adjacency matrix. This word came from adjacent. Adjacent means neighbors or the connected nodes. So if you see that, if you want to define the connections of N1, N2 and N3, so how many connections it can possibly have? We can define it like here. using this adjacency matrix. For example, we do like this, and 1 and 2 and 3, and here also and 1 and 2 and 3. So here so this will be, if there are, let's say, 3 nodes we have, so the matrix will be, okay, it doesn't look like matrix actually, but I will make it here separately, 3 by 3. So it will be, if there are 3 nodes here, then there will be 3 by 3 matrix, okay. This I made just to show how it works, but it doesn't actually look like matrix, but it will give you some idea. So how it works is that it shows that the connection between n1 and n1, is there any edge that connects n1 and n1? So no, so it means this is 0. And I'm talking about this here, this graph. I'm trying to make adjacency matrix of this graph. And then we look for, is there a relation between n1 and n2? No, because n1 and n2, they are not connected using an edge. So there is no connection, it means 0 here. And then we see the relationship between n1 and n3. So n1 and n3, they are connected by an edge. It means they are adjacent, they have a connection, so here it will be 1. Now we go to node 2 here, and we see from node 2 to node 1. Is there any connection? Node 2 to node 1. From node 2 there is no connection to node 1, so it means it is 0. And then node 2 to node 2, there is no connection, means it's 0. And then node 2 to node 3, node 2 to node 3, there is an edge here, there is a connection, so we say that this is 1. And similarly we go to now node 3 here, from node 3 to node 1, is there any connection here? Look at here, node 3 to node 1, yes, there is any connection, so we put it here 1. And then we check from node 3 to node 2. Node 3 to node 2, is there any connection? Yes, there is an edge. We put it 1 here. And then node 3 to node 3, there is no connection. So we put it here 0. And when you represent it in actual matrix form, so it will be like this: 0, 0, 1, 0, 0, 1, 1, 1, 0. So this is your matrix representation of the adjacency. So here you can see that sometimes if the edges are only directed edges, for example, this edge, let's say it is directed, it only goes in, there's a direct arrow here, okay, and then you can then it means there is only connection from n1 to n3, but there is no connection from n3 to n1. So in this case, n1 to n3 here will be 1, but n3 to n1 here will be 0. So here, this is also the difference between the directed graph and undirected graph. If you remember from your lecture, we studied about directed and undirected graphs. So this is how you can make. So if this matrix is from a directed graph, then these two entries will be also be 0, and only these two entries will be 1 here. I hope this concept is clear, and now let's move again to Matlab. Okay, what we now want to do, we have defined the nodes, and now we want to show some adjacency between these nodes, the edges of the nodes, using adjacency matrix. So we manually, because here we have five nodes, so it means that there will be a 5 by 5 matrix. So let's make them all first fully connected in the graph. You remember they all are connected, let's say, because here, if you remember, here we said that here the graph is only partially connected. For example, n1 is not connected with n2. So if this graph is fully connected, it means that each and every node has a connection with each other. So if n1 connected with n2, n2 connected with n3, and all nodes are interconnected, it means this is a fully connected graph. Okay. So at first, let's make it a fully connected graph here. So we say that, okay, 1, 1, 1, 1. Let's write 5 times 1. And then a semicolon for the next row. So this matrix should be, because we have 5 nodes, so this matrix should be 5 by 5, 5 rows and 5 columns. This is a second row, this is a third row, this is fourth row, and this is fifth row we have. And finally we put a bracket here, so that now this is a 5 by 5 matrix having 5 rows and 5 columns, and all the entries you see there 1. It means all the nodes are interconnected. All the nodes are connected by each other. Okay, so if you want to now visualize how it looks like, how this our, so now we have nodes, and also we have their edges or their connectivity. So it means that now we have a graph available. So our basic graph requirement is fulfilled. To visualize this graph, we can enter here figure. Let me write down here. Okay, so you have to write this command. It's called gplot. And then you have to give it your adjacency matrix, and then you have to give your nodes, and after that you have to type here what you want to print here. And then finally a semicolon. Okay. Plot the graph. Okay, let's now plot it, and let's see how it looks like, how our graph looks like. Okay. Okay, I think there is an error. Clear all with small c. So this is how our graph looks like. See that we have node number 1, 2, 3, 4, 5, and we have their coordinates. Node number 5 has a coordinate. This is node number 5 here, and see it has a coordinate of 5 along x-axis, 5 along y-axis, and similarly the other nodes also. You can see the coordinates of all 5 nodes here. And then one more thing, after that we have defined the start node, which is this node here, node number 1, and then we have a goal node here, which is node number 5 here, which has the coordinates 5, 5. So this is our goal node here. Our adjacency matrix, this is a 5 by 5 matrix, fully connected, all ones, no zeros. It means every node is connected with another node. So let me zoom it for you, make it bigger for you. You see that each node is connected with all other nodes. So node number 1, it is connected to node number 2, node number 3, node number 4. These are the edges we have. Edges means there is a connection. If there is no edge here, it means there is no connection between these two nodes. Okay. So node number 1 is connected with all other nodes using these edges, and then we have node number 2. It is also connected with all other nodes. So they are all interconnected. So this is a fully connected graph. Okay. So I hope that this is till now this is clear, and this is also easy to implement. So now you know how to make a graph manually, how to plot it also, and now we move forward. Okay, so after that, now we have a graph available, and now what we want to do is that we want to implement, we want to use Dijkstra's algorithm to find the shortest path in this graph from our start node to the goal node. Let's say we don't know the shortest path, and we need Dijkstra's algorithm to find the shortest path. Remember, Dijkstra's algorithm requires some cost of the edges, or the weights of the edges. If you remember from the lecture of Dijkstra's algorithm, it requires it also works on unweighted graphs, but for this example we take an example of a weighted graph with cost on the edges. So this is, let's say, node 1, then we have node 2 and node 3. So node 1 and node 3 are connected with an edge. Node 2 and node 3 are connected, and it has also not only connection, but it also weights. Let's say this is 3 and this is let's say 5 we have here. This can be a cost, this can be also distance, anything. The main thing is there should be some kind of weights. So now what we do, we implement Dijkstra's algorithm to find the shortest path. In this small graph, it is visual that only one path exists from n1 to n2, let's say we want to go. But if there are more nodes, if there are more number of edges, then of course we cannot do it by ourselves. We need some kind of algorithm, for example Dijkstra's algorithm, to find shortest path in weighted graphs. So this is an example of weighted graphs. and these are the, you can say these are the cost, or it is also, you can see that this is weights. I hope that this is clear. Okay, so we have now we have adjacency matrix. Now we define the our cost matrix or weight matrix, because for Dijkstra we need that. We must need the cost of the edges of the graph. Here this matrix only shows the connectivity. It shows either the edge is present or not, 0 or 1. But the actual cost or the weight of the edges is defined in this matrix. It's called cost matrix. And here you can define it manually. So let's say we have it must be of 5 by 5 also, because our nodes are 5, so matrix must be 5 by 5. Okay, so one thing we're gonna implement it, that if we know the cost of the node, then we say that okay, it means that we shall write it here like we did here for the adjacency matrix. But if there exists no connection, okay, and then we write the cost to be like very high. Okay, so first make it like let's say 1 1 1. Let's make it first all equal. It's like an unweighted graph. Third row, fourth row, and fifth row, and finally we put a bracket here. So this is our cost matrix. At first we say that okay, they all have some kind of same cost, so this is an unweighted graph. And after that we use Dijkstra's algorithm, which says we have a distance and we have path, and then we call this function that we have downloaded, Dijkstra, and here we have to define put your adjacency matrix, and then your cost matrix, and then your start node, and then your goal node, then close the bracket and semicolon. So here we call this function Dijkstra, so this function Dijkstra here, we are calling this function with some input arguments. So we already know all of them, but what we don't know is we don't know the path and the shortest distance. So where this function is located, this function is located here in my current folder, and this is actually Dijkstra's algorithm developed by some other person, and it is available. You can download it from internet. I've already mentioned the downloading link, and there you just go and download it, and here we just use it here. Okay, so now we have used the Dijkstra's algorithm, a function, and it will give us this path and the cost of this path, or the total distance. And now it's time to plot this path. How can we do that? First, this path is like an array. We have to take a transpose. So this I know from experience that it will give here an array with one or two rows, and there will be multiple columns. But what we want, that we want two columns and more rows, similar to like we did it here, like our nodes. Like there are more rows and only two columns. Take a transpose of the path. How can we do that? We say that, okay, path is equal to transpose of path and semicolon. So now this command will convert the more columns into more rows, so it is compatible with our nodes. Okay, after that we have to now, because here this Dijkstra's algorithm, it will give us the only path in terms of number of nodes. Okay, it will say that, okay, you have it will say node number 1, node number 2, node number 5, but it will not actually tell you the coordinates of these nodes. Okay, so to plot the nodes, actually you need coordinates. You don't need the number, you need the coordinates. So when you have the number in an array, for example, where are the nodes? Here, let's say, open it. So this is our nodes. So the Dijkstra's algorithm, it will say, okay, the shortest path is from node number 1 to node number 4. Okay, so now you have to get the coordinates of node number 1 and node number 4, x and y coordinates in this array. So for that we can do like this. The command is like, you have to just use a for loop for j is equal to 1 to size of path. So whatever the path we have obtained from Dijkstra's algorithm, okay, so then we use this size of path and we run this number of time our for loop. Okay, so we call it path 1. This is our new path, having actual coordinates, x and y coordinates of a node, not only numbers. Okay, and here we can write like j and all columns here. it should be like this. Yes, now this makes sense. Okay, so is there an error? It shows some error here. Nodes path. So this is to extract the x coordinate of the node, and this is for the y coordinate of the nodes. You see that we have what we do. We have the node number which is in the path, okay, and that we get from the Dijkstra's algorithm. And then we use this number to get the x coordinate of that node from the array that we stored here in our workspace, or that we defined here. So when we know the node number, let's say node number 3, and we come here and we get first 2 and then we get 3, and we put it here. This is, there will be 2 and then y component will be 3 here. So this command will do that. And this here, it's the jth row, and both the two columns x and y, they will be stored in your new path, which is path 1, or let's say path new, or path xy. I think path xy will be better. Okay, now we get the x and y coordinates of our path, and we end the for loop here. And after that, what we do, we again make a figure, and we use hold on, and we again gplot here a nodes, and then O, and then we plot our actual path. Path xy means all rows we have to plot and only the first column. From here, when we have this path, okay, it has multiple rows and 2 columns, okay. So when we want to plot it, so first we have to plot the x coordinates and then the y coordinates, okay. The x coordinate will be all rows and first column only, and then comma, and then we have path xy, all rows and second column. And then you have to define the color, or let's define the marker maybe. The length should be, we have to define the line width. Line width means that how thick your line should be. So line width should be 2. And then we have to marker. What type of marker we want to use, this is also important. So let's make the marker as O, or the circle, and then we have to define also the color. Let's make it red. Red 0 0. For red, the first one should be your 1 and the other one should be 0, because it's the format of red, green, blue. Okay, now we can end our bracket maybe. And yes, we have to define also the marker size. And let's make it 5 and finish it. So this till here the plotting is done. Just we add a comment here. Plot the path, plot the graph and path, or the shortest path. I think we have to add a comment here also. So what we did here, we get xy and get xy coordinates of nodes from the node number. Okay, so yes, it's very basic, but it looks fine. So let's try to run it and see the results. Okay, it seems like there is some error here. Gplot, okay, yes, where is a gplot here? Gplot. Let's run it again. So yes, we have here, you see this is our graph here. This was our starting node and this was our target node, and these are some other nodes here in the graph. And Dijkstra's algorithm have found the shortest path, which is a straight line. Of course, it makes sense. And the reason is that because the first reason is that it is a fully connected graph. So every node is connected by other node. So it means that it will always follow the shortest path. But if it's not a fully connected graph, let's say if this edge was missing, this edge was not there, that direct edge, then the algorithm will be forced to go to find some other route maybe. Okay. The second reason is why it has found the short straight line is that we have used a unweighted graph. The cost of the edges, it's same for all edges, and also it's 1. So it makes sense that this will be a shortest path, because according to Euclidean distance, the straight line is the shortest distance between the 2 points. So yes, so this was the simplest, I would say. So this was our original graph here on the left side, and this is the red color is the shortest path. Now let's try to make the graph a little bit complex. We started by changing our adjacency matrix, and we say that, okay, let's say there is no connection between node 1 and node 5. Okay, if you look at our adjacency matrix A here, You see that here? The shortest path that the algorithm has found was from node 1 to 5 directly, because it was 1. What if we put here 0? It means there is no connection between node 1 and 5. Let's see what happens now. So we have to put here 0, which shows that the first row and the fifth column, here we have to put 0. It means there is no edge between first node and fifth column. Okay, so here first row and fifth column here. So now we try to run the algorithm and see what happens. See that it has now given a different path. Although it still shows the edge between 1 and 5, which is actually not true. Let's see if it is an error or why it's showing this edge. I'm not sure why it's, I think this gplot command, it shows inherently, it shows all the edges, but I'm not sure. I shall read about it further and then let you know. So let's check it again, our adjacency matrix here. So we said that we defined that there is no connection between first node and the fifth node. And yes, here is a mistake. We define only one way connection missing. But how about the connection between node 5th and node 1? Here we also have to define 0. Okay, you understood that? So the edges, they are, because this is an undirected graph, to make it directed, you have to change it, both values to 0, not to make it directed, but to completely remove the edge. You have to here also tell it 0, because here we said that first row and fifth row has no connection, no edge, and we have to here also tell that fifth node and the first node have no connection. But for this, the one we made it was a directed graph, because it's only one direction. It says that the first node and fifth node has no connection if we go from 1 to 5, but the fifth node and first node has a connection if we go from fifth node to first node. So this is a directed graph. If we put here 1 also, then it will be undirected graph. And if we want to completely remove the edge, then we have to here also put 0. So how we can do that here? So the fifth row and first column here also should be 0. Then our gplot will now plot. See that the edge is now missing. So the connection between 1 and 5 is missing. There is no edge here. So now the Dijkstra's algorithm finds another possible shortest path, which is through some other nodes. Okay, and if you want to see the cost of this path, here you can see here the total distance is 2. Traveling from it means traveling from 1 to this node. It requires a cost of 2. And if you see now the adjacency matrix, so it has no connection between node 1 and 5 and 5 and 1, 0. All connections are 0. So this is how we can manipulate our adjacency matrix to change the type of graph to make it directed, undirected, fully connected, or partially connected, whatever you want. You can change here these values, and you can get connectivity between different nodes here. Okay, now let's try to also now change some values between. There is another way how we can remove the connectivity between two nodes, and this is how we can do that. For example, here let's take this graph here. Now this is an unweighted graph. It means each of the edge has same cost, and the cost of the edge is defined here in our cost matrix, which is 1, 1, 1. All have the one cost. And if you see the cost matrix here, you can see the cost from moving from first node to fifth node is 1, from node 3 to 3 is 1, and node 5 to node 2 is also 1. So this is an unweighted graph. Now let's try to make it weighted graph, and we let's say our robot want to move from here to our goal place here, and Dijkstra algorithm says this is our shortest path if we consider all paths same weights. Okay, but there is a problem. Let's say problem is that here the path between this node and this node, the road is not that good. There are a lot of jumps, the road is broken, and we want to avoid it. We don't want to completely avoid it. We want to say that, okay, if there are alternate paths, then try to go another way. So what we do here, we just increase the cost of this path here. Now for example, it's 1. If we want to make it less desirable, we increase the cost of this path. Okay, we make it like 10 or 100 or 1000. So now what will happen if we make it a higher cost? Since Dijkstra's algorithm always finds the shortest path with minimum cost, so what will happen? Dijkstra's algorithm will come here, and then it looks okay. It looks here that okay, this is very high value. It will avoid it because Dijkstra's algorithm finds the minimum cost. It will go like from here, or maybe it will totally go another path. Let's see, and let's try to implement this high cost value. So what we're going to do is we shall make the cost between this node and this node higher. Let's implement it. So these were our nodes here, and if you remember, this was the output of our Dijkstra, and it says that go to node number 1, 2, and then 5. Okay, and then these are our actual nodes here. Node number 1, the coordinates of node number 1, node number 2, and node number 5, the XY coordinates. So what we now gonna do is we shall increase the cost from node number 2 to node number 5. Previously it was 1, and now we shall increase it. Let's go to our cost matrix and see. Going from node number 2 to node number 5. This is node 2, and we want to go to node number 5. Here we have to increase the value, make it higher, like 10, 100, or 1000. Okay, if you want to avoid this. Alternative, you also have to do from 5 to 2 also, from here to this value also. So we have to change these two values. So no second row and fifth column, and fifth row and second column, we have to change both values in our cost matrix. So this is the first row, this is the second row, and fifth column. Here we, let's say, make it higher, make it 1000, and then we have to, this is third row, fourth row, fifth row, and second column here, make the cost higher, 1000. And now let's run it. See that it has voided. Previously it was going like this, and this is node number 2. This was 1 to 2 and then 2 to 5. But now since we have increased the cost 1000, but the other edges have the cost 1, 1, 1. So now what will happen? The Dijkstra's algorithm always finds the shortest or the minimum cost path. So it has now chosen another minimum cost path. Although there are other alternatives also, but this is the one it has chosen. So this is how Dijkstra's algorithm works. This is how you can find a shortest path in the graph. Now let's see our C matrix here. See, we have 1000 and 1000 here. The cost is higher now. And if you see the output of the Dijkstra's algorithm, it says that go to node number 1, then 3, then 5. And if we read our path, these are the coordinates of node number 1, node number 3, and node number 5. And similarly, if you see the total distance traveled, the cost, it will be 2. Going from 1 to node number 5, it costs 2. And if you see the adjacency matrix this time, so it's almost connected, but only the first and the fifth nodes, they are not connected. We have put their adjacency value 0, so there is no edge between 1 and 5. If we put edge between 1 and 5, then it will be directly go from 1 to 5. So yes, so this is how we implement the graph search algorithm and to visualize. I hope that you have learned today what is adjacency matrix, what is a cost matrix, and how we can use Dijkstra's algorithm, what are its inputs and what are the outputs it has. So inputs, we have the adjacency matrix, cost matrix, then start node and goal node, and the output is a path which contains a sequence of nodes, node numbers, and then its cost, the total distance. And then we learned about how we can extract the coordinates of nodes from node numbers. Here we have used this for loop. And then finally we learned how we can plot a graph and also our path on top of the graph. So this is the end of our lab session, and what you have to do is now, it's your task to this is you have to do now by yourself. I shall give you the code, Matlab code, and you have to try to implement this. You have to find shortest path in the following graph using Dijkstra's algorithm. This is a graph you have to make. So first you have to define your nodes, their XY coordinates, and then you have to define the adjacency between the connection or the edges. And then in the cost matrix, you have to define the cost of between different edges. Okay, and then you have to using Dijkstra's algorithm, you have to plot the shortest path between the start and the goal position. So this is your task you have to complete. I hope that this lab session is helpful in understanding how Dijkstra's algorithm and how the graphs work. And if you have any questions, you can always contact me by email, or we can also have a live session on Friday for 1 hour. So we can also discuss. If you have any problems, any troubles, feel free to contact me. Thank you very much.